Hát üdvözlök mindenkit, welcome everybody. Szeretnék az első kérdéssel, ez itt a Rust Hungary első meetupja, az enyémben látszik is rajta, hogy ez itt az első meetup. This is our first meetup, so you could feel it probably. Kérdés, ki az, aki nem beszél magyarul? Bocsánat, angolul. Ez egy hülye kérdés lett volna. Ki az, aki nem beszél angolul közületek? Jó. Who here cannot speak Hungarian? All right. So we have. I'm going to switch to English. Innentől kezdve angolul fogom tartani a bevezetőt, illetve az előadásaink nagy része is, ha jól tudom, így nincs értelme valószínűleg. Mind a három előadásunk angol nyelvű lesz, de minden előadásról felvétel készül, és ezek magyarul feliratozva meg fogjátok találni az interneten, tehát hogy ezt ha valamit nem sikerül megértenetek, akkor kérdezzetek, illetve utólag is tudjátok majd ezeket nézni feliratozva. So I'm switching to English. All our presentations will be recorded today, and they will be subtitled and uploaded to the internet, to the official Rust channel. So you can catch up if you missed any of this today. So we're going to have 3 talks today, starting off with Florian. Florian is a co-organizer of a bunch of conferences around Ruby and Rust. He's one of the main organizers of RustFest, which is the first European Rust conference, and is a huge community person from Berlin, doing a bunch of conferences and other conference organizing and community organizing. He is going to give us an intro into Rust today. So give it a hey.
Yeah, so hello everyone. The reason why we're here is basically nothing works technology-wise, and basically we've got an idea how it could be made better, to have other ways how it doesn't work. Faki already introduced me. I'm Florian. This is basically all my profiles. If you want to be me for a day, just take this, put it into your bash profile, source it. He already introduced me. I'm a backend developer by trade. I'm currently getting into Rust training. I've been a Ruby programmer since 2013 and Rust programmer since 2003, no, the other way around. So basically all languages that start with RU are good for me. I have a tiny little company. I'm a community person for ages. I founded 2 Rust user groups. I founded the Search user group in Berlin, and I'm the chair of Ruby Berlin e.V., which almost no one knows, but which is the largest nonprofit for Ruby in Europe and has also been supporting the Eurocode conference and all these kind of things, which is happening here in Budapest next week. I'm sad that I'm going to miss it. I organize a couple of conferences myself, the Eurocamp and JRubyConf EU Ruby conferences. I'm organizer of the RustFest. I'm part of the global Rust community team. Rust has a special team that's just for managing community. It's all by community members, so it's not a Mozilla thing or something. And yeah, happy to be part of it. As a hobby, I shoot arrows at stuff, so mind that during the Q&A. But yeah, I'm here to talk to you about Rust. Rust is a new programming language aimed at systems programming. It is powered and was developed along with Servo, which is a new browser engine in development by Mozilla. It's a research browser engine, so it's probably never going to be a full browser. But a lot of technologies and a lot of approaches that are found in Servo are now coming into Firefox. I was trying to say slowly, it isn't that slow, they're going to hit in November. So this is an interesting thing. Rust is a programming language that was always developed in lockstep with a large project, a large practical project, side by side, which is unusual. Usually the largest project in a programming language at the beginning is the compiler or the interpreter. With Rust it's different. The browser engine has most of the time been larger than the language implementation itself. It is there to provide an alternative to C and C++, but also to other high-level languages. This is a common mistake that people make to think, well, this is a C replacement. It isn't. It is also meant to bring new stuff to other programming fields. But yes, mostly it's built for the same area that C and C++ are built for, programs with type control over memory layout and all of these kind of things. I also have to say that we are seeing this as an evolution and not as kind of a fight with C and C++. There's a lot of good things that these languages made, and I think the best thing I ever heard about Rust is finally a new programming language by people that understood what was good about C. So the 3 points that Rust is trying to make as a language, it wants to be safe, concurrent, and fast, without any kind of trade-offs to make. Like, this is safe, but it isn't concurrent. This is concurrent, but it isn't fast, and all of these kind of things. It actually aims to bring these 3 under one umbrella. And we've seen all of these promises before, but how do we differ? Rust has a certain set of core features that are very interesting and also very new, which gives the language the air of being very hard. It isn't, it's just that a couple of core features of Rust are genuinely new and not present in other programming languages. So if you're picking the language up, be prepared that there's a certain part you have to grok instead of porting it over from another language that you already know, because some of these things are not present in other languages. But there's a couple of things that you do have from other ones. We have a static type system with local type inference. If you have a program, Haskell or any kind of other programming language that has a static type system where you don't have to type all the types, but it finds out what the type of an expression is, and you don't need to put it on every variable. This is basically how it works. In a little bit, with a little twist, Rust doesn't infer types at any kinds of boundaries. Like if you have a function, you need to state the whole signature. It doesn't infer it. And this is a conscious choice for programming language or for program stability, that these are the boundaries where we say, this is where you actually have to note it down what the interface is. It has explicit mutability. I come to that in a second. It has something that we call zero-cost abstractions, which is we have abstractions that look like lots of modern high-level programming languages have, but we aim for these abstractions being so well optimized that you couldn't handwrite them better by hand. And finally, we have runtime-independent concurrency primitives. I come to why this is interesting in a second and explain them in detail. It has explicit error control flow. There are no exceptions, but all error cases must be handled. It has no null. It has no concept of a null pointer. Values have to be there, and if they're absent, there's a special value for that. It has something that we call static automatic memory management. It does automatically manage memory for you, so you rarely explicitly deallocate, and it doesn't leak memory. But that happens all at compile time. It doesn't have any kind of runtime garbage collection as you would have it in Ruby, Java, or even D. But when programming, it feels like these kinds of languages because we have a type system that can actually deduce the points where this needs to happen without you as a programmer explaining it. So it feels like you don't do allog and deallog, but it actually does all that. So no garbage collection and no runtime system, which brings us back to this is a systems programming language. It doesn't bring a runtime or any kind of baggage with it in your resulting program. But it's built with practical use in mind from the beginning. As I told you, it was used to build a browser engine, and there was always this feedback loop of the browser engine needing language features and the language features being built for the browser engine, which means that a lot of these features weren't created in like, oh, this could be useful in some use case, in some abstract use case, but most of the time the use cases were actually there. And there were other feedback loops, like an older version of Rust actually had a garbage collector. And people didn't actually trust that this language, like this core concept of running without a garbage collector, would fit at all places. And the way to prove that this was actually possible was porting the whole server code base over to not using the garbage collector at all. And when that worked, you could actually write a practical, huge program in the programming language without this kind of backdoor where you could actually use a garbage collector. This was used as a proof that this was actually possible. So there's a lot of decisions in Rust where people come and say, oh, why are you not doing this? We can actually say, oh, we did do this. We found out that it wasn't good. A lot of features in the language are there for the long run. I'm going to explain that a little through the talk, but that sometimes means that if you start learning the language and you're writing small programs, some of the features might not have that much bang as it would have for people that are writing larger programs. So there's always some kind of mentalizing necessary on how would that feature look like if I would use it on a large code base. So we are kind of hesitant to introduce features just for being there to make it easier during the first 2 days, which doesn't mean that we don't want to be an ergonomic language. So if you can introduce ergonomics that make the language better on day-to-day use, for sure we're doing it. It's just that the core idea of language is around we're building large software. We're not writing hello world programs all day. And that also comes to, we have great tooling and documentation. Mozilla actually employs people to just write tooling for the language and to just write documentation for the language, which means that our standard libraries are almost completely documented in more than just 2 sentences per method. And we have a whole book written on the language. It's currently being rewritten. It's close to completion. It's usually better than with other new programming languages. So what does a language look like? Who here programs C or used to program C? Oh, not that many. Java? Okay. So it's basically a curly braces language, which doesn't look too non-standard. It does a few things that, for example, Java and C wouldn't do. Like it has this kind of matching on a type that has multiple alternatives. So you can say, if you open a temp dir, here just as an example, I'm just creating a temp dir and I'm opening a file in it. For several reasons, file system gone, whatever, opening a temp dir could work or could not work. And this is what I mean by Rust has explicit error handling. What happens if you open up a new temp dir is you get a type back that says it worked or it didn't. And you actually need to check on this. So you can branch your code on, okay, this worked, and this is the directory. And then you can do whatever with it. So you can create a file in it using the path and joining the name on it. It's all pretty standard. Or you can do something if there's an error. And then you can say, well, couldn't open the temporary directory and throw another kind of error. An interesting thing here is, and that's what I mean by static automatic memory management, I'm opening a file handle here, which for proper working of the program, I need to close at some point. Rust will actually notice that at this point, this file handle falls out of scope, needs to be deallocated, and the file needs to be closed. So it automatically handles this case for us and all kinds of similar cases. So in that sense, that's what I mean by it's kind of like you're working in a garbage collected language that has these kinds of semantics, but this has no runtime component. The compiler will notice that the temp file runs out of scope and will deallocate it and will close the file handle correctly. I'll start first with zero-cost abstractions because they're basically just this. Rust can look much more high level than the thing before. Like this was pretty much by the numbers. You go top to bottom, and if you know all the operations, you're in imperative programming land. But Rust has a certain functional component, especially in its APIs. So what I can do here, as I said, the first operation can fail or not fail, and I can start combining these operations and can say, okay, I want to open a new temp tier, and then, which will be executed if that was successful, and then do with that temp tier, create a file in it, and so on and so forth. So I can start combining things. But the way where this plays into zero-cost abstractions is our compiler is so smart that basically this compiles, these two things will compile to the same program. And this is actually not the Rust compiler being extremely smart. This is something that LLVM, the core technology that we use, can do since ages. So we're basically just piggybacking on that and actually using it in a programming language. So let's start with the basic concepts that I mentioned that are a bit unused to people. So one of the basic concepts of Rust is mutability. Nowadays, many programming languages cover by mutability by either saying everything's mutable and all bets are off, or mutability is evil, so nothing's mutable, and everything works like it wouldn't be mutable, and the compiler may be optimizing in the back where it knows that something works better by mutating a memory region instead of you explicitly doing that. Rust has a different idea there. It actually makes mutability an explicit part of the language. So let's just take two structures. This is basically like C or many other programming languages that have bare memory structures work. You just have a structure with fields in it. There's not much to it. So I have a structure that has an inner structure, inner data, which has a number, just as an example. I can create that in my program, basically by just using the initialization syntax here. And now I will try to go to the inner field and set the value to something different. And this won't work, because by default in Rust, everything's immutable. But I can make it mutable. I can use the same program and say, D is mutable. And then I can mutate it. So mutability is part of all variable bindings, of all interfaces, of all signatures. This is just a simple example. The compiler will actually reason about the mutability properties for several reasons that I introduce. And this is the base concept that you hit on first, and that will get a little weird, like during the first few days where you're trying to learn the language: ownership and borrowing. These are concepts like borrowing is something where the name was basically invented in the Rust world, but ownership is something that, especially in the C++ world, is definitely something which is used in lingo. Question is, who owns memory, and who owns part of a program that owns memory needs to care for allocation and deallocation, and everyone else should not touch it. Because that's basically what happens when there's a double free in a C program. Two parts of the program disagree on who's responsible for erasing that memory region, and they do it both. The other way around, a memory leak is no one feels responsible, no one removes that memory. Same thing. And what Rust says is that every piece of data that you introduce into a program is uniquely owned. There's only one owner. And this ownership can be passed on, or it can be borrowed. And here you have mutable and immutable again. I'll come to what borrow is quickly. And the thing with passing ownership is, if you pass ownership to a function that takes ownership, you cannot use it afterwards. Classic cases here is you pass on a file handle to another part of the program. You shouldn't use it afterwards because you don't know what happened. File might be closed or something. This is standard programming semantics with thinking about giving something away to another part of a program, or basically lending it away and trying to do something with it afterwards. And the other thing that we allow is this kind of borrowing. What borrowing says is you give away access to something, but you're keeping it. The way it works memory-wise is once you pass away ownership, you pass away everything to that piece of data, access, mutating, you're not allowed to do anything anymore. So the flow in this program is I instantiate data, I give it to taking ownership, and the compiler will introduce a statement here that removes it from memory. Once it falls out of scope where it is owned, once the data falls out of scope where it is owned, it will be removed from memory. And the trick here is the uniqueness. Every piece of data is uniquely owned. That means once a handle on owned data drops, you are sure that you need to remove it from memory. It's basically reference counting for people that can only count to 1. Count up to 1, count up to 0, gone. And that is something that a compiler can do for you, because the semantics of the language forbid it, that it's possible to get a second reference. And then we have share immutably and share mutably. The thing with borrowing is it gives away access to the data, basically by handing out the pointer, with two different kinds of semantics. Either you can just get it and you can read it, but you're not allowed to write it, or you can get it and you can mutate it, and then the calling code must be aware that it could have been mutated. And there's a couple of rules around that, and that's what I mean by the compiler or the Rust language actually uses the mutability information that you give it. The first thing is you can borrow mutably only once. Why? Concurrency problems. It's totally safe to borrow something mutably to another part of the program that doesn't have anything running side by side. As long as you know that something might mutate the data, it's perfectly fine, but there's no other party that could concurrently mutate it. Or you can borrow it away multiple times immutably, which is also fine because there's no collisions that can happen because the language semantics force that none of the receivers of this data can actually mutate it. And this is exclusive, so either the first rule apply or the second. So it's not possible to once share it away mutably and 100 times immutably, because that would break the expectations of the ones where you borrowed it immutably, because this means it's exclusive, there's no other part of the program that could mutate it as long as you know that you have an immutable borrow. And this can also be used for optimization by the compiler later. And mutability runs deep, and that's one of the things where I say like Rust is built for large programs. This applies deeply through all your code as big as it is. Like you can throw an immutable pointer in a 100,000 line library, you are sure that it will come out not mutated. And this is a common source of bugs in larger programs, that someone thinks, oh, no one's mutating that, I'm going to flip this bit. And it's part of all signatures, as I mentioned. And the idea of this is, Rust makes reasoning about large systems localized by reducing action at distance. That doesn't make it the fastest language in the assembly of those large systems, but once you're in a method scope and you know this I can mutate, this I can't mutate, this no one else can mutate, why are you working here? You can work fully localized in a block of code and having much more information than you would have in another programming language about the context in which this code runs in. Which brings me to the last hallmark feature that I would like to show. I'm sure unable to introduce like the whole language in this little talk. Just like the good parts, or let's say the good parts, the parts where the language is genuinely different. So, advanced concurrency checking. Let's take this little program. Because there's sometimes places where you would like to share stuff more than once, Rust actually has a reference counted pointer. It's standard RC. And let's say we have a method that just takes a pointer to a number, increments the number by 1, and yeah, that's all it does. Let's take this code and run it in a concurrent setting. So we run 3 threads that start calculating on that number. So let's take a ref counted integer. We just take an integer, put it into a ref counted pointer. This is how we get multiple handles on this. But now let's spawn 3 threads and increment it in each of those threads. The error here is pretty clear if you ever worked in a concurrent setting. The problem is that there's no kind of moderation that ensures that these 3 increments will actually happen each after another. And incrementing an integer on a processor in a concurrent setting isn't a secure operation. What could happen is that 2 of those operations are running at the same time, and one of those gets lost. So after running this, the integer might be 2, which is not, 44. It should be 46. Rust actually detects that. Rust carries along with all types information, whether they can be shared through a pointer between threads, mutably shared between threads, or if they need to be sent over. Sending over meaning it needs to be copied to the other side to any other concurrency primitive. And this is what the compiler tells me here. By the way, a reference counted you can't send over the thread boundary. Yeah, all kinds of bugs can happen there. And what Rust does there is it annotates all kinds of data with 2 informations. Is it sendable or is it syncable? Sendable and syncable means the first can cross boundaries by being moved to the other side, which is basically passing ownership between 2 threads, for example. If you send something to another thread, you're not allowed to handle it anymore. It exclusively goes to the other side, which is basically the idea that is behind Erlang, or also the proper handling of go-go routines. And the second, less sharing in between those. So, for example, if you would wrap something in mutex and make sure that this moderation actually works, to make sure that all of these 3 operations run one after another, this gets into the Rust type system as well. But because Rust is a systems programming language, it doesn't tell you which strategy to use. It also doesn't tell you that you actually need to use threads. This would also work in any kind of other asynchronous setting. This is a very abstract view on these things, but something that the compiler can enforce and can give you as an information. Yeah, it's independent of the concurrency concept. It doesn't impose any kind of approach, which comes back to Rust as a systems programming language. If we would impose any kind of approach, you couldn't write most low-level systems in that. We actually want you to write one or the other. If you choose Erlang, for example, you would have to use the first approach, which comes with its own share of advantages. If you use Erlang, you don't need to think about all these things so hard. But this gives you the ability to think about all these things safely. And this is one of the things that is behind the new style system in Firefox, which was that basically computing styles on a website is something that can be theoretically very well parallelized. But because these systems are so huge, they're full of concurrency bugs when you actually do. And a little bit of the magic sauce behind that is that the compiler in these cases would actually tell you if you do something unsafe. And you don't need to run it using any kind of other static analysis tools. Like Firefox has a huge static analysis tool just written for their old style system that just works on the specific kind of C++ they write. And if you don't, it even stops working to detect these kinds of cases. And here the language brings it on its own. And we have libraries on top of that, providing threading, channels, event-based concurrency. So if you want to use something that is like Go channels, we actually have an implementation of this. There's two very important libraries on this. The first is Tok.io, which is our async event reactor, and Rayon, which does parallel processing of large lists of data. So, and the language gives you low-level control and safety. Borrows that I just mentioned are basically just pointers. The ampersand notation isn't in any way random. Yes, these are references like they are in C. And values are plain values, just like you would have them in C. So structures have not like methods bound to them or something like this. The language gives you the possibility to opt out of the safety if absolutely necessary. There's a special kind of sublanguage that's called Unsafe Rust, or that's off, but you can do everything that you could do in C. So if any of these semantics are problematic at any point you can switch them off. You should do that for good reasons. At the beginning, it's pretty often that people switch them off because they don't know the right equivalent in Rust. This is kind of dangerous, but there's a lot of use cases where we just need that. For example, device drivers have memory locations that your language can't abstract, but you know about them, but you know that they can basically be mutated at any time, which doesn't quite fit Rust's system of you decide if that's mutable or not mutable. Unsafe is just for that. There's sometimes people say that unsafe Rust is something you should do. Absolutely not. It's a part of a language for all these kind of reasons. A low-level programming language needs low-level access. It's just that Rust's idea of this is you wrap that into a safe program, like you wrap that into a safe interface, and make sure that you give an interface that holds all guarantees around it. And it's something that is rather rarely used. I think Servo has around 2,000 lines of unsafe code in a code base that goes into the 6-digit range. Our ops engineer coined the phrase, safe code means that you can take better risks. So there's, especially the style system that I've seen has optimizations in it where you're like, okay, I don't know if I would like to do this with war pointers. Like if you can even keep that in your head. Like it's a multi-10,000 line program and throwing around pointers in very complex data structures. Finally, Rust provides higher level abstractions through generics and traits that's similar to C++ templates or Java generics. Just to show you what the code looks like, we are not inventing new syntax here. So if I would take the thing that I had before and say I've got this inner data that wraps an integer, and I just say this struct is generic over something, some value I, and I say the inner value is I can just create that like I did that before, and just have to notate that this is data that wraps an inner data, and the compiler will actually figure out what the proper layout for this is. If you have a program in a language that has this angle bracket notation for generics, Java or C, C++, this comes quite naturally. And what I mean by local type inference is, in this case, you actually don't have to notate the variable because in the instantiation, you already see this is data, inner data, and the language will find that out by itself. Usually, you don't need to annotate any of this within any kind of method body, as long as you can infer it from the outset. And finally, there's the last thing that I would like to mention, which is the concept of lifetimes. I used to not have it in this presentation, but people complained because I didn't drop the name. The weird thing is I usually don't program with them. I am doing Rust for 3 years now, and this is the feature I rarely use. Because it's pretty often more arcane than you would believe. So what lifetimes do is, anyone sees the problem in this program? If you would translate it to C, if you would make the ampersand a pointer, would you see it then? So the problem in this program is, I have a number that I instantiate here, and I'm returning a borrow on that number. But because of the ownership rules I explained to you, if I have let number 3, and the scope ends, number falls out of scope, it will be deallocated due to the ownership rules. But I'm returning a borrow on it. So if that were legal, that would lead to an illegal memory access because number might be deallocated. This is the classic case of dangling pointer in C. And Rust doesn't allow that because it will actually tell me number does not live long enough. It will actually point me out where in the code it happens and how long number would live until the end of the scope. And the problem that beginners have here, and that's why I started to mention it, is now they start like, how can I extend the lifetime of number? You can't, because that's the ownership rules. What Rust does here is it actually tells you you're breaking the rules, program differently. You can allocate the number on the heap, or you can return it, like in the case of an integer, you can just return the bare integer or something, but never hand out a borrow on something that you might later remove from memory before the borrow is not active anymore. And that leads to this very weird statement. They have a learning curve, but they are a very simple concept. Because the only thing, the biggest problem is that people assume they do more than they actually do. They are purely descriptive. So the only thing that this lifetime, the concept of lifetimes does, it says, this lives so long, this lives longer, and the borrow lives longer than the thing that you're borrowing, that isn't possible. That's all that lifetimes do. You can actually compile Rust code without taking any care of these at all. Like there's a compiler that does none of this checking. The code is completely valid. The information is only used for validity checking of the code. And that's a problem that people run into when they are like, I'd like to program a lifetime. No, you can't program a lifetime. You can't find any kind of description of this problem or of this kind of code where this is possible. And that's the thing that people bang their head against once they run into this error. So if you ever run into these kinds of problems, the first thing you should say is, what am I expressing? Because this actually catches the weirdest kinds of bugs where you're sitting there for a quarter of an hour and then you're like, oh yes, in this case, this would actually suck fault. And the second is, you should just think like, how can I write this differently? How can I express it differently so that my memory actually stays valid all of the time? Don't start throwing around like lifetime annotations and all these kind of things. So, just as a quick glance into the language. So, the second part that I would like to talk about is like, how do people actually get into Rust? And this is not like me dreaming up ways how people get into Rust, but actually why are people adopting Rust and on which path? First of all, should you use Rust? Definitely yes, in my opinion. It brings along a lot of very interesting new concepts, especially like the whole concurrency checking. I don't know in any other adopted language. There's languages that have concepts that make this whole thing easier, but a language that actually checks your patterns on how you are working concurrently in their type system, I don't know any, except research languages, obviously. One thing I have to say, Rust is not a simple language. Whoever tells you otherwise is wrong. Especially because the features are built for the long run. It takes a bit of time to click, but I also think this is a good thing. The new things are worth it. Like the complexity of the language comes with a lot of things that you probably have never been exposed to, but that give a lot of things, a lot of food for your brain. I know a lot of people that say, learning Rust made me a lot better in my C++, for example. because like all of these kinds of sharing semantics, also like if you write Java, a concurrent Java, thinking in these kinds of sharing ideas and these kinds of passing on ownership is definitely useful in object-oriented languages as well. Rust in itself, like the ecosystem though, is rather approachable. It's easy to get an environment set up. We have a lot of documentation for all operating systems, for all larger operating systems on how to do that. There's great docs through our book, and they're almost fully documented standard library, but probably the parts that aren't documented you won't hit quickly. And it has built-in dependency management, just like you would know from JavaScript, Ruby, or something. We have like a proper way of doing this. And it plays very well with others. It interfaces with C or any kind of C foreign function interface almost at no or zero cost, depending on how expensive the C interface of your language is. That's why I wrote at almost no cost. Like if, for example, the Ruby CFFI isn't zero cost. So the cost of using that, Rust doesn't fix. But you can, for example, if your language has a CFFI, you can use Rust with it. And this is a path where a lot of people go into Rust. There's more people that I know that have rewritten critical parts of their Ruby applications in Rust than I know that have rewritten critical parts of it in C. But everyone says, oh, if we get performance problems, we drop down to C. But no one ever does it, because if you seg faults within this small library that you wrote, you're bringing down your whole web server. No one wants to do this. If you work in a seg fault-free language, which Safe Rust is, this is a totally feasible and testable thing to do. So even with people that don't have an ample amount of experience with system programming, they can do this. With C, you need someone who's properly trained in having all of the ways to handle this. There's binding generators for C and C++, and they're surprisingly good because, well, Firefox needs them. And Firefox is using Rust in a lot of places now, and this definitely improves the quality of those libraries. There's high-level bindings for some languages. Ruby has a binding that's called Helix. JavaScript has a binding that's called Neon. They're all maintained and really good. So you don't need to be super into how does the FFI of my language work. And it's a great partner. It preserves the conveniences of high-level languages like seg fault freeness, memory management, and all of these kinds of things in low-level land. And we also don't want to be a primary language at all costs. Don't rewrite your whole application in Rust. But we want to be the best secondary one. So if you have any kind of complaints of the range, like, we tried to adopt Rust for this little task that we have. We're very interested. We're very, very interested. We're not fully interested in people that are like, okay, I started out with a huge application and I wrote it all in Rust. That's just a very tough call for language that's just 2 years old. If you're doing this, we definitely support you full way, but most of the users that adopt us are secondary language adopters, and this is definitely something that we fully support and want to know all the issues that you have. So it's built for gradual adoption. And it also shows in the projects that are using Rust. The GStreamer framework, video framework, is using Rust for, you can now fully write GStreamer applications in Rust. So will Firefox, obviously. Facebook has just rewritten a Mercurial server in Rust for performance problems. They're using Mercurial heavily inside. There's a whole operating system written in it. And this is not a fun operating system. Like, this is a proper operating system that boots into a graphical shell that is usable. There's also educational operating systems, 3 or 4 of them, and there's even one for embedded use cases. And there's also an implementation of RTFM, which is real-time for the masses, which is a concurrency framework built for embedded applications. So if anyone does embedded applications, Rust is moving there. Sometimes, if you're working on a very specialized processor, probably you haven't got an implementation for it yet. That is feasible to do, but someone's got to do the work at some point. And yeah, GStreamer is currently introducing Rust, mostly for plugins. And their findings were Rust has better ergonomics at the same speed, like performance-wise. Their 20 last security issues were memory bugs, because especially video software, is heavily parsing file formats and streams and all these kind of things. They're very prone to memory issues, and Rust makes sure they don't happen. And they found they had a huge source of bugs, especially in their multi-threading code. So any kind of support for better multi-threading is right up the alley. And they needed a language that gives latency guarantees that GC languages just can't give. GC run just means that your stream's going to be hitching. You really don't want to have that. And it runs well in memory-constrained environments. So we don't have large concepts on top of every value, like a vtable or something. Rust in itself has a commitment to stability. Rust is released every 6 weeks, which is a bit odd for a programming language. But it is very nice because, in the sense that every of those releases won't introduce many changes. And we got a strong commitment to backwards compatibility and a lot of huge machinery to ensure that, including pulling down all public Rust code and trying to build it and seeing if there's regressions, if we feel that this could introduce a regression. And that also means we're currently at version, this is outdated, we're currently at version 1.21.0. So you see I gave parts of this presentation before. Yeah, so it means it makes it very easy for you to also stay on the newest version because you're not going to have to rebuild the whole world. Also, every kind of unstable feature we don't allow to be used on the stable channel of the compiler. The reasoning being that we don't want to de facto standardize them. So a lot of times programming languages have this unstable flag or pragma that you can activate that are not in the language standard. We have that, but only if you're using the nightly version of the compiler to ensure that people don't actually build stable software on top of that, which takes us the ability to change these things. But it's also surprisingly mature for such a young language because code generation is provided through LLVM, which in itself is mature. It's the base technology behind the Apple Clang compiler and all these kind of things. It has no runtime. Having no runtime means we have no runtime bugs in our runtime. This used to be a huge problem with our garbage collector because the garbage collector was bad. Sorry, this was a research implementation. And just throwing it out also meant we don't have to write one. And we have a very conservative approach to actually to adopt something into the standard library. We really want to make sure that this is something that holds for the ages. It is also, if you do any kind of embedded stuff, Rust is by default a cross-compiler, and the whole toolchain, that's the advantage of shipping the whole toolchain, is aware of that. So you can install in 2 or 3 commands, I want to have a Rust compiler with the standard library for Apple iOS, and all these kind of things. There's almost no setup in the cross-compilation. If your target has a specific SDK that you need to use that we can't ship, you need to install it by hand. And it supports embedded use cases, so we are there for several kinds of embedded processors, Cortex-M being the most prominent one. The compiler provides useful errors and warnings. We changed that a lot. We want every of those warnings to not be arcane. Some still are, but that changes in future versions. And we have a currently in development language server for supporting IDEs. There's also IDEs that already have great support, especially IDEA has great support for Rust, but they ship their own tooling. Still, it needs to be said, it's a young language. So the library ecosystem is in flux. People pick it up, write their library, sometimes drop out, sometimes someone takes over the library. Some other libraries are surprisingly well maintained for ages already, like our JSON implementations and all of these kind of things are top notch. Yeah. So most important libraries are available for many protocols, HTTP, ECC, parsers, parser libraries are there in masses, and a couple of concurrency abstraction libraries for the most important parts. So you don't have to build your event reactor on top of send and sync. You don't really want to do that for every kind of program. We have that. It's just not in the language And there's currently a huge ongoing effort to bring libraries close to 1.0 to 1.0, which is just a community effort where we encourage people of libraries that have wide use to actually find contributors that would bring them to a stable 1.0 release that they will actually be willing to maintain. What we already have, we have pre-built binary libraries for 48 different kinds of targets, so Cortex-M, iOS, what do I know? We have full and advanced build tooling through our dependency and build management tool, Cargo, and we have WebASM support, which will be talked about in a second, so WebAssembly. And it's an A+ product. Every commit goes through a huge testing process. We rarely have regressions. We do have regressions, but also contribution is very easy. So our median time for contribution to the compiler to go through or to any kind of our core projects is 6 days. That's the median time. So if you have just a documentation fix, it's probably through once the maintainer wakes up, except they're on holidays. And if you've got a larger change, that might go up to 20, 30 days or something, but this is the time range we're talking about for where small to large changes to the language land in, and we make sure that people that have small changes don't go through a huge process that's built for like making sure that the stability of the language gets maintained. If you're just fixing a small mistake somewhere or a typo, this is something we just want to have you through. And this works really well. So there's lots and lots of infrastructure around CI, quality control, and development. And the language itself usually built since version 0.4.0. And that's something that's very interesting. Mozilla has a research department, and Rust is out of the research department, but that research department expects all of their projects to be in a releasable state all the time, and to actually make proper releases all 2 months. So when we were in the alpha ages, there was still a release every 2 months to make sure that the software is releasable. And that totally shows in how Mozilla builds their software, that this is not just some researchers bashing out like very bad code that no one ever can retrace because they cannot build it. And by build, I mean check it out, make, done. And this works since 5 or 6 years. So Mozilla support there helps really. But there's one thing I should say, when it comes to governance and community, Rust is not a Mozilla project. And this is a conscious decision. Actually, most of the changes to the language and most of the contributions to the language come from community members, around 75%, even code contributions, even though there's many people employed at Mozilla full-time to do Rust and to work with Rust. There's a lot of community effort behind it, and Mozilla is really well set up because they're doing that for ages to also handle this in a fashion that doesn't feel like this language is just going this way because Mozilla wants it. They actually tell you why they're doing it, and also support ways to use the language which are not Mozilla's use case. For example, they are funding someone to make Rust better in embedded, and Mozilla currently doesn't do any kind of embedded development, as far as I know. And to have that, we also have a public RFC process, so any larger changes to the language will go through a process with a debate. And if you want to have your voice heard, this is the place where you can do it. And it is not unusual that these RFCs fail. Like there has been one RFC for a larger rebuild of the module system of the language that failed 3 times over the summer. People were getting really frustrated on both sides, but like it just didn't end up somewhere where we felt like this is good to be done in that state. It's now through on the fourth try, and this is good because I think the 4th try is really the best one. So we have a friendly and active community, but we're also supporting commercial users. So if anyone's using Rust in a commercial setting, we try to get interviews to hear about their issues. This is not because we think companies should have exclusive access, but companies often have an interest in not being too public about many things or about the software that they build. So we give them a trustable way to approach us. And they have problems that probably the open source community currently doesn't have. So this kind of gives us an insight into what larger usage of the programming languages might have problems with. And we have companies that do consult, develop, and train. Yeah, finally, commercial users here are Mozilla. Dropbox has built huge parts of their backend in Rust. Facebook, as I mentioned, Chef and Habitat. So Chef has a new product called Habitat, which is completely written in Rust. And we've got a theater that's actually using that for our productions. So, final words. In my opinion, Rust is not a hype at all. A lot of the community growth is very natural. It's actually not as fast as maybe media would make you believe. It's very constant. And it's bringing safe programming to targets where it was previously unfeasible. And I think this is the interesting part about the language. And it's totally a language that wants to be used, that wants to be practically used. But we also bring, like, this whole concurrency checking thing is something where it gets really interesting even if you were using a high-level language before. So, and finally, we had our annual survey. We do annual surveys every year, yes. And we had it this summer, and interestingly, the strongest sub-community of Rust is Europe. Rust is totally, like, Europe is totally into Rust. It's by a good margin, and I'm very happy about this. So it isn't like a language that sweeps over from the US to Europe and then over there. But there's huge communities outside of the US, also in India, and that makes me very happy there. So, finally, that's it. Thank you.